So here in this tutorial, I will go through the exercise 4 in RMCProfile tutorial on the Mac platform. So first of all, on the Mac platform, with the new package for RMCProfile, we add in the capability. Basically, we packed up the whole package in the DMG format, so you can drag into the application folder and launch the program very easily. So here in my case, I configure the Windows key plus the spacebar to open the so-called alt-right search capability to search for the RMCProfile. But in your default search functionalities with the Spotlight, you can also do the same thing basically, to open the search bar and type in RMCProfile to launch the program. So here I just launched the RMCProfile program, and we are going to focus on the Exercise-4. So we go into that folder, and furthermore we go to the FabK subfolder to focus on this temperature point specifically. So the very first thing we want to do is to prepare the structural configuration for the refinement for RMC fitting, and also the Brock profile or data which will be needed by RMC to do the fitting for the Brock data. So we then need to go into the Jesus folder, and here in this case we are using the old Jesus1 program for this tutorial, and in nowadays we have also some other programs available there to do the refinement, like Jesus2, which is the modern version of Jesus, and also, for example, we have Topaz as well. And we have interface for in RMCProfile for those programs as well. For example, for Jesus2, they have dedicated session in Jesus2 package to do the preparation for RMC fitting. And also they have dedicated tutorial about how to do that. So I will put a link below this video to link you to the tutorial by Jesus2 team. And also we also have the Topaz interface as well, so you can find my email address in the developer page of our current web page, and you can just reach out to me at any time if you want to use the Topaz interface to prepare the Brock fitting. So first of all, anyways, let's start with the Jesus1 program, and here what we want to do is to run the so-called data-to-config command to prepare the RMC6F configuration. Given the structural configuration we output from the Jesus refinement. So in this case, we are using the TBL file, and because here in this case you can notice that we also have the EXP file, which is the main control file of Jesus1 program, if you are familiar with it. So these two files, the EXP and the TBL file, is with the same step name. So when you run this single command, at the same time it reads in the TBL file to prepare the RMC6F configuration, the structural configuration. At the same time, it will also read in this file, the EXP file, to prepare the Brock profiles, which will be needed for RMC to do its own fitting. So let's just run this command, and then let's inspect the output. So all these new files you didn't see before are just created by this data-to-config command. And here you can also see the RMC6F structural configuration file. So those are some files that we need for RMC fitting. So that's the first thing we want to do. And the second thing we want to do is to go outside this folder and copy all the necessary files concerning the RMCProfile fitting to the current folder to do the further fitting. And to copy those files, definitely you can use command line commands like CP on Linux platform, or if you're more familiar with the GUI interface, you can just open the current folder in Finder, for example, on Mac, and then you can just copy the files as usual. Say in this case we want to copy the RMC configuration file, those two files, into say the 5K folder, and then we want to copy the files in Jesus folder, and in this case we are going to use this second bank data from product data from Jesus refinement. So we copy the _2 back _2 product, and also the .inst file, which representing the instrument parameter file, and also together with the RMC6F structural configuration. So we copy those files into the 5K folder. Okay, so now we got those files, including both the DAT file, as you have already maybe seen in the first 3 tutorials. This DAT file is just the control file for RMC to do its own feeding, its own job, and dedicated .dw file representing the distance window configuration, which you can find in the menu. That is something to do with the distance window constraint, basically to specify a minimum and maximum distance for each specific atomic pairs in the system. So the next thing we want to copy is for sure the data file. So we have the control file, the configuration file, the block files, but we are still missing the total scaling files, like these two, the f of q file and the g of r file. So in the documentation, I mean in the tutorial documentation, you will find a section that about which data you can use. So the first trial is to use the data without rescaling. So basically what we call the rescaling, what we mean by rescaling is that we want our data to be on absolute scale, because we are not doing approach like PDF GUI or whatever small box way of doing the refinement, which is based on the parameterized approach. So here in this case, we are based on numerical approach, so that requires somehow our data to be on an absolute scale. And given these two data size is not on an absolute scale, and we can use the so-called stock STOG program that comes together with RMCProfile package to do this rescaling job, to go into to go from this unscaled or improperly scaled data to this properly scaled or absolute scaled data. So that's the two data we want to copy into this main folder. So that's probably all the things we need to do the further RMC feeding. And then we, as instructed in the tutorial, we maybe can create some folder for the first try, and then just cut those files into this first try folder. So that's just like a container for whatever we are trying to do. So we go back to this command line and type in go into the first try folder. And before we really kick off the RMC feeding, one thing we have to do is to rename these two files, because you can see that this .back and .block file is not with the same stamp name as all the other files, but in RMC6 it is required for those files to be with the same name with the main control file. So we have to rename it to something like this back, and then we do the same thing for the block file. So now it should be fine. If before the refinement, we just open the main control file to see what we have. And the thing I just want to mention here is that here we set the time limit to be 10 minutes. So the whole program is supposed to be running for 10 minutes, so the CPU hour, I guess. And with the 0.2 save period, which means every 0.2 minutes it will read out the RMC6F configuration and a whole bunch of other like output files all together. So I won't go through all these different sections about different data size. You can, according to the keyword, you can just find corresponding introductions in the menu. So let's come out and then just execute the RMC fitting by putting the RMCProfile command together with the step name, and then just oh sorry, yeah. So in this case, if you remember, I just mentioned that in the first trial given by the tutorial, it is trying to use the data which is not properly, or which is not on absolute scale. So the file name here is somehow wrong, so we have to add in the _sc representing scaling. And again, I just want to mention that if you don't like, here in this case I'm using the Vim editor to do the editing of files. If you don't like that, definitely you can go back to the Finder and open the DAT file with whichever editor you prefer. And in this case, let's kick off the running again, and hopefully it should be running. And as you can see, it will be, it's already starting its running. So here I will probably just pause the recording and then wait until the fitting is finished, because it's gonna take a while. So here the fitting has been finished, as you can see from the command line prompt. And if you're interested in checking out this command window output, you can run something like this if you run directly from command line without using some job submission or management tools. You can run something like this, for example, using the greater than sign to redirect output in some files like test.out, and if you like, you can run the whole command in the background under Linux operating system. So that's just in case you want to check out the whole output once while the program is running. Basically, it contains some information about the data scaling, normalization, and chi-square for different data size, and so on and so forth. So that's something I want to mention briefly. And you can check out all the generated files here in this running folder. And the first thing we want to inspect about the fitting is for sure the fitting quality. And then to do that, we are going to use this new, again, plotting program called RMCProfile, and followed by the step name of these files. So here in this case is strontium titanate _5K. And so this plotting program is based in Python. And to use this, I guess you have to install the Python environment and together with the matplotlib, and that's probably the only thing you're going to need to enable this, to be able to use this plotting program. And for example, we can inspect the fitting quality for PDF, which is not too bad, and also we can check the SFQ, which is also not too bad, and probably the broad data as well. It's not perfect, but it's not too bad as well. And considering we just run for 10 minutes, so it does have some space to improve. But anyhow, this is just a demonstration of using this little program to do this plotting for inspecting the fitting quality, and then we hit on the exit to exit the program for plotting. And then the next thing we want to inspect is probably the structural configuration. So to do that, we first want to transform the RMC6F configuration generated from the fitting to the format that we're going to use to plot the structural configuration. And the program we're going to use here is called Itemi. So that's a free software that comes together, again, bundled with RMCProfile package that you can use to view the structural configuration. But the first thing we want to do is to transform the output structural configuration in RMC6F format into a format that is recognizable by the Itemi program. So we just run this program and put in the RMC6 file we generated from the feeding, and then enter the mass. Those mass are not values are not necessary for doing the plotting, but it's just required by the itemi format. So we just put in the strontium 88 and 48 for titanium and 16 for oxygen. So you can see it's done its job. And if you check the output, you're gonna find the _i.cfg config file that is going to be recognized by the itemi program. So then we can just use the itemi program to plot the output structural configuration in proper format. And then we execute the command and wait a bit for the result to show out. Oh, a size. Okay, so the atom coordination maximum number is exceeded. So that probably means we have too many neighbors. And that's because when we do the format transformation, where is the file? The default length here you can see is basic length unit for the configuration, so that's probably too small, so that the distance are calculated to be too small, so that we have a lot of atoms actually surrounding a certain atom. So that's definitely not right. So for the plotting purpose or visualization purpose, we don't need to change that value to be accurate, so we just want to change it to something bigger than 1, like 10 in this case, and let's see whether that will work. So you see that it works, it does work. Although the atoms may look a little bit small, so once you open the program, you can use the mouse to rotate and to zoom in and zoom out, and probably press the B button. Sometimes it's working, sometimes it's not. I'm not sure why, but usually when you press the B button on the keyboard, it will add in the bounds to this configuration. Oh, I see probably why, because we changed the unit length to be a little bit larger. So given some default value for the bounding information, it's probably not going to recognize any real bounds because the distance now is not right. But anyhow, so supposing the distance is somehow right, we can just press the B button, and a whole bunch of other things you can check out from the itemi website about how to manipulate the structural configuration to see something useful for you, or just plot the configuration for putting into documentation or something like that. Once you are done with the visualization, you can press the Q button from the keyboard to exit the program. So that's about the visualization of the structural configuration. And the very next thing and the last thing we want to do is to do a little bit more useful analysis. And in this case, in the tutorial, we put in the instructions and tutorial for the GUSP program, which is a little program that can be used to analyze the polyhedral, basically, environment, rotation, tilting, and stuff, as compared to the standard, for example, equilibrium structural configuration, to see how the structural configuration is distorted as compared to the equilibrium positions. So to do that, let's just go into upper level and go into the GUSP folder. And to do, so you see here, I have already done analysis for doing this tutorial before I start recording the video, but it's fine, so we can just overwrite those files. To do the analysis, we need two files. One is the RMC6F configuration we generated from the feeding. The other one is some sort of standard RMC6F configuration which we are going to compare to. So basically, we just need these two structural configuration files, and also with the main control file to run the GUSP program. And in this case, we are going to use this strontium titanate _GUSP .cfg again representing the configuration. That's the main configuration file for the GASP program. And to compare to RMC6F configurations, one thing we want to do is to copy the RMC6F generated from the RMC feeding. We just try it out. So in this case, we want to copy in the RMC6F configuration from the running folder to the current folder, and we just name it like this. So that's the file generated from the RMC feeding, and we have already got the standard or cubic, in this case, configuration which does not contain any like distortions as compared to the equilibrium positions. So here I have already run the command to transform the zip file to the RMC6F configuration, but you can also run it on the outside, like in this case. We just copy in the command. And specifically for Mac OS, especially in the new Mac OS, sometimes you probably need to include those square bracket in the double quote, because in some cases in the new OS, the square bracket is recognized as special character, so the normal command will not work. So in this case, we just run this command to generate the RMC6F file. You can see that because we have already got RMC6F sitting there, it will just put the new configuration into this file, and then we just copy this file over to replace the old one. So now we have everything. We have the two RMC6F configurations we're going to use, we are going to compare, and the main configuration file or control file for the GASP program. And then we just kick off the GASP analysis. So before we do that, we need to transform again the RMC6F configuration file to a format that's going to be recognized by the GASP program. And to do that, we again have a bundled program called RMC2GASP together with, within the RMCProfile package. So once you are in the environment of RMCProfile package, you can just run this command without problems. So you see that it will ask for the input file, which is actually the RMC6F structural configuration file. And then it's done, we run the command again to prepare the same thing for the cubic structure. So now we have everything, and here is specifically in this case we're going to need these two DAT files generated for each configuration. So you see that this one for the RMC6F configuration after the feeding, and this one is the original corresponding to the cubic phase. And then that's pretty much all preparations we need to do before we run the GASP analysis. And then probably you can open the control file for GASP, and then you can see those keywords. And to know about what those keywords mean, you can refer to the GASP menu or in the tutorial folder of RMCProfile package. And here I don't want to go into details about those keywords. Basically, it's just to do some preparations before we do the structural configuration, and then to do the final comparisons between these two structural configurations. And once we got that, everything is ready, I guess, and then we just start the GASP command, and it will ask for the configuration file, and in this case we just put in the configuration file name without extensions. So you see that although it's spaced out some error message, but I believe and also I think it should be already mentioned in the tutorial, it's just some funny humor by the developer, and those message does not mean the program is not running successfully. Instead, it is running successfully, and you can see that this is new generated sorry, I messed up something there. But anyways, this is the file that is generated after running the GASP successfully. And to further visualize, let's basically compare the contain the comparison between these two structural configurations, and that we can use to do some further visualization to see the comparisons. But before we see or visualize the comparison results, basically containing this guy, we again need to transform that guy into some other format so we can just directly obtain the rotation and tilting angles, something like that, to visualize. And to do that, we have again a bundled program called get Jesus rotors, basically to transform that comparison file generated by GUSP into the rotation angles, basically along X, Y, and Z directions. So to do that transformation, we need to run this command to transform the comparison file into the three rotation files, here in this case along X, Y, and Z directions. And one more further step is to transform those guys into histograms so we can just plot them. Because if you open those files, it's not it's just containing a whole bunch of rotation angles. We want to turn those whole bunch of rotation angles values to histograms, basically to bin into different bins along the x-axis representing the rotation angle, and so that we can just plot XY diagram. And to do the transformation of to the histogram, we are going to run the histogram data followed by the data file. So in this case, we run the X, Y, Z directions one by one to generate the binned or histogram data, which we can just directly plot. And to do the plotting, we're going to use the program again bundled in the RMCProfile package called data-mplot, and we followed that command by the three files we just generated corresponding to the rotation angle along X, Y, and Z direction in this case. So we execute that command and we see the results. So that's the plot we finally see, and which is also mentioned in the tutorial. So I think that's pretty much all for this exercise 4. It's a little bit lengthy, but I hope it's making sense to you all. Thank you.